Hey everybody, welcome back. In this video we're going to work on a population exponential growth. Here's our formula. If It's really the same formula you had a minute ago with P equals E to the RT. It's just dealing with, I guess in this case it could be bacteria or something like that, so they didn't use P, they use N sub 0. N of T is the population amount. So, using the same language here. R is the relative growth rate expressed as a percentage of the population. Sometimes it's done that way. Other times they talk doubling. A lot of times they'll talk doubling. And when they do, then your rate is the natural log of 2 divided by h, where h is the doubling time. Now, it might seem weird to use h as a doubling time, but I did that because we have another formula where half-life in h makes sense for that. And this one is the same formula, only you have a negative exponent, one of them. So we'll use that letter so it'll be universal between the two things, okay? And let's take a look at one of these problems, see what it looks like. Now, remember, this is the same thing as a P e to the RT, and here's how it reads. It says, in a lab experiment of 2,200 bacteria are placed in a petri dish. The conditions are such that the number of bacteria is able to double every 26 hours. So this is a doubling formula. Right? It's doubling, we know that. How many bacteria would there be after 17 hours? All right, so this is asking for an amount. This might actually be a little bit of an easier problem than we've been working on, because it says how much or how many is a little easier to work with than saying how long when you're solving for t. That gets into a logarithmic equation. One thing we do need real quick is to calculate this r, and that's the natural log of 2 over 26. And I don't have it. I did that in the last video, didn't I? I think I'm so slick sometimes. So let's just do it like this. All right, so we need R equals the natural log of 2, and it's going to be divided by the half-life time, which is 26 hours. And when you do that, I don't like to approximate a whole lot, but I'm going to just put this in as an approximation. You'll see that when I really calculate things out, I'll let my calculator carry the decimal for me if I'm doing something like this. But I get 0.02666, okay? And that's the rate we're going to use. So let's do our calculation. Really, they're asking me to, for n of 17, and now we know the rate. So there is no equation to solve here. This is just filling in and using a formula. So what we're really looking at here is n of 17 equals the initial amount, e raised to the 0.02666 times 17, right? Because that's our independent variable. And let's calculate that real quick. Oh, it looks horrible, doesn't it? Okay, so we have 2,200. Oh, just real quick, to show you what I'm talking about, letting the calculator do the work for you. So if you said the natural log of 2, and you divide that by, say, what was it, 26, let it carry that number for you. Then you're going to put in your 2,200, and you're going to use E here. E to the, go up here and grab it, put it in. Now we're going to multiply that by the 17. And notice the accuracy it kept for me is a lot better than me approximating that number. So after 17 hours, it looks like we would have 3,461. So I'm just gonna call that approximately 3,461. 3,461. Okay, pretty simple problem, and I think you'll find this next one's not much harder. There's a radioactive decay formula. Now it's strikingly similar to what we just saw. M sub 0 is the initial mass. Okay, so what happens with radioactive decay is a lot of times they'll have a half-life. And that means half the mass disappears in so much time, and they know how much that'll be. If m sub 0 is the initial mass of the radioactive substance with a half-life h, then the population at time t is modeled by the function. Now notice this is a lot like your other formula, only it's got a negative exponent, which means this is a decaying formula. And again, if it's a half-life, it's usually natural log of 2 over h. So it's such a similar formula. They're really the same thing. So, oops, that's not what I wanted. Let's get some space here. All right, so element X is a radioactive isotope such that every 16 hours, its mass decreases by half. There's your H living right there. Given the initial mass of the sample is 5,900, that's m sub 0, how much of the element would remain after 27 years? Again, this isn't even solving for t. It says how much, so they're giving me a far easier problem than the other ones we've done. So we have the natural log of 2, and we're going to divide that by h, which is 16. And what does that give me? Looking at my cheat sheet, I admit it, I've already calculated some of this out, otherwise this video would just take too long. Approximately 0.043321. Okay. Now again, we're going to plug that number in for our rate, and we can solve it just like this. We're going to go, okay, we're looking for m of 27, right? M of 27 is the initial amount, 5,900, E raised to the negative, don't forget the negative exponent, 0.043321 T. You're telling me it's 27, and we need to calculate that. Let's see what we get. We'll put approximate there before we go. And let's go to our calculator. And again, we're going to do the same thing again. I'm going to let the calculator carry the value for me. Natural log of 2 divided by 16. That's going to become R. All right, there's that number we've recorded. Now we're going to say we want our 5,900. And I'm going to get my exponential here. I'm going to say negative. Put that, don't forget to put that in there. Now I'm going to go up and grab that guy and put him in. Times 16. Nope, it's not 16. I'm about to screw this thing up, y'all. 27. And that gives me about 1,831.7 grams remaining. So we'll say it's approximately 1,831.7. And one thing, if you're talking half-life, you're saying, well, does that even make sense? Okay, so if half of it remained after 16 years, half of 59 would be, notice 1,800 is a lot less than half of 59, right? That's half of 36. So when we look at it like that, we can see that, yes, we have gone more than a half-life, and it makes sense that this should be less than half of 5,900. I hope you're thinking of, if you think of it that way, kind of give you an indication if you're even in the ballpark. So that's how you solve these couple problems. You got some of these in Delta Math to do. I'm just giving you a heads up. They're really easy, and I think you'll do fine with them. I got one more problem to do with you in this section, and I'll see you there on Newton's Law of Cooling.